Thank you, Sunshine. It's really just such a delight to be here because this is a really unique audience. We get as biologists to talk to a lot of different groups, but as Sunshine describes it, here today we have a group of journalists who I had the pleasure of working with a little earlier today, people from the public and researchers here in the nitty-gritty of doing marine science, right? And so in some ways we have everybody at hand that needs to be part of communicating what's happening in the oceans, studying what's happening in the oceans, and actually changing what's happening in the oceans. So it's a really exciting audience to speak with today. So the process, we were talking with this journalist group earlier today, the process of doing science is sort of interesting one. The sort of general MO, modus operandi for scientists is that you'll latch on to some piece of some question or hypothesis of interest to you. You'll study it for months. More likely you'll engage and study it for years. You sort of put together this synthesis piece in a journal publication, and then you send it out and hope it does something. Quite often what it does is it sits right in the stacks of these journals. And so, you know, I do what I've always done is when I feel like I've done something I'm proud of, I call my mom, right? So I call her and I tell her, hey mom, I just got a paper published in ecology. Hey mom, I just got a paper published in the Proceedings of the National Academy of Sciences or whatever it is. And she says, that's great, where can I go get a copy of this? Can I run down to Barnes & Noble's and get a copy of PNAS? Unfortunately, the answer almost universally is no. Actually, you can't get a copy of these journals. That you're just going to have to take my word for it, Mom, that this is something exciting and new and you need to be proud of me. There are some exceptions. I'm going to talk about a body of science that I did today that with collaborators, we basically engaged the question of what is the past and what is the future of the oceans going to be? You know, an exciting set of questions. And that landed on the front page of the New York Times. I think all of us in the room would agree that we wish we could see more marine science on the front page of the New York Times, but perhaps this is a good start. This was really encouraging to me because what that said was that people were deeply curious and deeply interested in these questions about past and future of the oceans. How do they engage? Where are we headed in the oceans? And so that's kind of what I want to talk about today. Now, by and large, scientists don't take on the business of describing gigantic futures in sort of one go, right? As a physicist may write sort of to public audiences about what the sort of future of the universe is, they don't on a day-to-day basis actually study the future of the universe. You break off one small piece of that puzzle and study it to death, right? And so my piece of the puzzle, just by way of introduction before we launch into some of these bigger questions, and I'll actually hopefully show and segue how my own personal research interests got me into this kind of broader senses of these broader kinds of curiosities. My own research interest is understanding how size structure changes in communities, in living communities, in ecosystems, in ecological communities, and what that means for communities. So life, if you think of it as a whole bunch of particles, can be packaged in small forms or it can be packaged in big forms. And just like in any other physical or biological setting, if you have big things or small things all orbiting around, the dynamics of the systems can be totally different. So the question at hand that I'm really interested in is what happens when you restructure the size dynamics for a lot of the ways that these systems operate. Does it change the way that energy flows, the way that nutrients move back and forth across communities? Does it change the way that interactions work in a community? It can sound a little bit esoteric, but let me tell you why it is I'm so interested in size structure, because we've really changed the size of life on our planet. So to illustrate this, I'm going to actually start with a terrestrial example, and I'll sort of ask you to transport yourself across the United States to California, to my home state, as Sunshine said, and actually transport yourself 12,000 years ago into a Pleistocene California. So this might be the view that you would see if you were walking around the hills of California 12,000 or so years ago. There are a few familiar faces in here, right? And by the way, this could be a very similar view for the eastern seaboard at the same time. Few familiar faces. You have raccoons up here, coyotes in the background, but by and large, this is a pretty foreign-looking faunal assemblage, a very foreign-looking set of animals. If we fast forward out of the Pleistocene into present-day California on this same walk, you'll see just those familiar faces remaining, but there's been a grand shift. And what's happened is that we've lost so many of the big members of these communities. We've repackaged life, as I said, in smaller forms. And so there's no way that that shift could have transpired in so short amount of time. 12,000 years in the grand scheme of things is a very short amount of ecological and evolutionary time. There's no way that that's transpired without changing the way that these living communities work. So my inroads to trying to figure out how can some of these changes take place are often kind of case studies. You know, I do some work in terrestrial systems as well as marine systems, but you'll go to somewhere like East Africa where there's lots of big animals left. You build these Jurassic Park style fences to keep them out of a space of ecosystem, and then study the changes that transpire in this elephant-free exclosure you've created. You go to some place in the remote part of the Pacific using kind of a space for time transformation, going back hundreds or thousands of years in time by going to an ultra-remote place where there are very few people, where there's very little fishing, study something like the world's largest parrotfish, and then infer from the observations in this more pristine setting where this large animal is present what the significance is of its loss in places where there are lots of us and a lot more of our impact. Or you study where these things go, or you use new tools to figure out when they get rare, where they are, what resources they're using, what habitats they're using, right? The problem is that we need to bring a lot of new technologies into this space when animals are getting, when these large and imperiled animals are getting more and more rare, because that's the very time when you need the most information about them. How do you actually protect them? So you need actually good scientific tools to figure out what they need as they become less common. Well, this business actually of focusing my scientific attention on a lot of these increasingly rare organisms makes me something like a biological hospice care nurse, right? What I'm doing in effect is focusing in on animals that may be sort of at the end of their biological lifespan. Animals that are on the brink of extinction, and even some animals that have already been driven extinct, looking backwards ecologically in time. And that makes me hypersensitive to these rates of loss. And the rates are quite frightening. How many of you have ever heard of the term the sixth mass extinction? Okay, so a pretty good awareness of this concept. Basically, the idea is, and this is actually a concept very important, that's developed from data that we've collected on land. The concept essentially is a story about rate, that we're driving species on land at rates that are on par with some of the largest extinctions we've seen in the billion-year history of our planet, right? So the sixth mass extinction suggests that we're engineering something that is number 6. There are 5 other mass extinctions that we've seen, and these things are bad, right? So we have the Perma-Triassic extinction, sometimes colloquially called the Great Dying, when something like over 90% of life in the oceans went extinct. We have the Cretaceous-Tertiary, Cretaceous-Paleogene boundary, when an asteroid hit the planet, knocking out the dinosaurs, right? We're essentially saying that on land, we're the new comet, right? That we're hitting the Earth with the force of something like that comet that hit during the Cretaceous-Tertiary boundary, something like a 11 kilometers long asteroid hitting the planet and basically shaking up the entire climate. That the rate by which we're driving species extinct now approximates some of those previous rates. But, as I said, this is what's happening on land. This is derived from observing extinction rates for terrestrial species. So what's the story in the oceans? Is the sixth mass extinction leaking into the oceans? And this was the sort of entryway into this science that I want to talk about today, this review of history and future of our impact on the oceans. There are lots of other things we try to cover besides these elements of extinction. Really what we wanted to get our head around was what are the diverse ways that we're changing animal life in the oceans? What are the history of those impacts, and how can that history inform a little bit about where we're going and what can we do about where we're headed? So in this article, which was a review in Science, we basically came up with this conclusion. I'm going to lay it out for you in advance, and then I'm going to try in the rest of the talk to exhibit or defend how we came to this conclusion. So essentially, we say here, humans have had a profoundly deleterious impacts on marine animal populations, but there's still time and there exist mechanisms to avert the kinds of defaunation disasters we observed on land. Defaunation is sort of the term we use to describe animal loss. It's kind of like the analog for what deforestation is to loss of plant communities, right? So rephrase this. What we're saying here is that things may be bad in the oceans, but they're not as bad on land, and there's a great opportunity for us to intervene. It's kind of an optimistic view, right? And you never actually know where your science, or you shouldn't know what the sort of answer you're going to get from your science as you launch it, right? Either if you know the answer ahead of time, you've chosen a boring question, or there's something else a bit awry. We didn't know what we were going to turn up with when we tried to produce this review. It was actually very encouraging to find out that we had something that was so optimistic. How do we jive this view, though, that there is a lot of vibrancy and life and potential for ocean conservation with a lot of the headlines that all of us read in the marine science community? Headlines like coastal sharks are collapsing, sequential loss of whales and other megafauna in the oceans, that the coral reefs in the world are in serious trouble because of climate change. Well, I wish I could say that we found that there were weaknesses in all of this science. That there are not. In fact, if anything, it made us hyper aware that so many of these headlines are in fact true. But it became an exercise of putting things into perspective. It became an exercise of describing the oceans or seeing the oceans in light of the impacts we've had on land, and that brings to light a kind of a glass of biodiversity that's half full. In fact, brimmingly half full, and that's the point that I'd like to make today. And you can see this optimism as you step through the title. You know, journalists will appreciate this. There's a series of titles that I think are attracting readers, and then you get to the optimism. Scientists see a chance to reverse the harm in the oceans and save species. So where is the optimism that you see in that title coming from? What's the data there supporting this? So let's walk back through an extinction timeline. Here is an extinction record. These are extinctions that humans have played a role in on both land and sea. The terrestrial extinctions are coded in green. The marine extinctions are coded in blue. So we'll start back about 40,000 years ago. There is a deeper extinction record with that, but it's a fine starting point. What we see is a footprint of extinction that basically follows our own footprint as our species moves from continent to continent. We arrive in Australia, there's a spike of extinction. We arrive in the Americas, there's a spike in extinction. We head all around the world, and there is this huge spike of extinction that people are calling the beginnings, potentially, of the sixth mass extinction. What's the story with the oceans? A lot of green on this graph. Silence, essentially, in terms of the marine extinction record, as we have played a role, until we get to the last few hundred years, right? So there is a good source of optimism. This, by numbers, if we look in just the past 500 years, the numbers are quite encouraging. 500 extinctions that have been chronicled on land in the last 500 years works out to be about an extinction a year. In the same time period, only 15 marine animal extinctions. You're looking at them now, oceans 15, right? Now, almost certainly, it's harder for us to describe extinctions in the oceans. It's harder for us to do science in the oceans. Everyone here appreciates that. It's harder for us to get information out of this boundary that we weren't sort of built to operate in. So it's certainly harder for us to get information on extinction. Imagine it this way. It took us 73 years to find the Titanic under the ocean, right? In fact, wasn't it somebody from Rhode Island that found it? University of Rhode Island. It took us 73 years to find a 1,000-ton, multi-thousand-ton ship, which is one of the most famous ships in the world. Think how hard it would be for us to find the last of a shrimp that may be in danger to determine whether this species is alive out there or the species has gone totally extinct. So there's definitely this kind of bias in terms of detection probabilities. However, I really think that this difference that we're observing here is quite valid. I really think that we're ahead of the game, or behind the game, probably a better way to put it, in terms of extinction in the ocean. So that's certainly a good bit of news. Let's look for biological interest and also for interest in terms of responding to this threat at where endangerment lies. So these are a summary of where different species, well, we clump them into kind of familiar groups, where this endangerment lies. So you have species that are extinct in orange, endangered in red, and then we have a group of unknowns that are data deficient, meaning that we've reviewed them, but we don't know enough about what that review says to make sense of whether they're in trouble or not, and a bunch of species we haven't got to yet. What can we tell through this portrait of risk? Well, one interesting thing is that species on this side that actually have terrestrial contact by and large are more at risk than species on this side that through their life history are exclusively aquatic. Makes sense if we're the risk factor here. If you put a flipper or a webbed foot on land, you end up in a higher risk category. So that's one informative thing. Let's look for other nuanced pieces of information. Let's compare cartilaginous fishes to ray fin fishes, bony fishes, right? So what this is telling us is that by and large, sharks and rays, cartilaginous fishes, are more in trouble than the rest of the types of fishes that we normally would engage in, right? And that makes sense biologically as well, because sharks and rays grow slower, they have less offspring, they have a kind of life history strategy that predisposes them to be more vulnerable to things like fishing. The last thing that I'd point out here is the whole, the high density, the high abundance of gray matter in that part of the graph. That's sections of, that's areas of marine biodiversity, of life in the oceans that haven't yet been reviewed, that we know nothing about. We're doing an excellent job about filling in these blanks. We just absolutely have to fill in these information gaps if we're going to be able to say something about risk and respond to risk. It's incredibly troubling that for fishes, which you think a very popular group, we have so many species that are unreviewed, and that's to say nothing of how behind the curve we are at assessing the status of marine invertebrates. All right, let me talk a little bit about the future. My pathway to talking about the future in the oceans is looking at a history of the oceans. What can a history of the way that we influence the environment, I'm going to talk both about land and sea, tell us about the future of our impacts on the oceans. My point, the point I'm going to make here is that there's a common sequence, a kind of ontogeny of the way that we influence the environment that may repeat itself in the oceans as it did on land. So in other words, by looking backwards, looking at sort of the history of our impact on land, that can be our best crystal ball for understanding the future of our impacts in the oceans. Let me explain sort of what I mean in this chronology. So step one in the chronology, I would say, is artisanal hunting. It happened first on land, bows and arrows, spears, a little bit of hunger, a whole lot of elbow grease. We were able to make a lot of impact on biodiversity on land. We, in fact, as I showed you in the extinction record, we're able to drive entire assemblages totally extinct. And remember, this is 50,000 or so years ago, using these simple tools. The next evolution in this chronology is moving from simple tools to more complex tools. We let go of the bows and arrows, replace those things with shotguns, and we now have mechanized tools like railroads to get our products out from the bush or the forest into cities' areas of consumption. That's step two, from sort of artisanal, simple tools to industrial scale hunting. And this transition was really important. When we adopted a lot of these commercial strategies, industrial techniques for harvest, we moved from being able to just tackle these big and conspicuous parts of animals in our environment to being able to drive some of the species that are most prolific on the planet extinct, right? Passenger pigeon is probably the best example of that, the victim of this industrial commercial trade in wildlife. The next evolution in this step three in this stage, as it took place on land, was a shift from hunting the animals directly for food, for pelts, for products associated with their own bodies, to hunting their space. What I mean there is that we moved into actually using habitats and changing habitats as a result of our own use on land. This happened very significantly about the time of the Industrial Revolution. We built farms, we built our cities, we built our factories that needed things from habitats out into the world with increasing rapidity. We switched from just hunting animals to actually using their habitats. So where are we actually, if this chronology works, where are we on this timeline in the oceans? Well, we started using simple tools in the oceans. In fact, we've been hunting animal in the oceans for a very long time, also about 40,000 years. There are some people that describe fully modern humans as being one of the fundamental attributes is our capacity to actually fish. So that's awfully old using these simple tools, but it took us a lot longer to get to phase two. It took us a lot longer to get to this phase where we're using commercial industrial tools to hunt in the oceans. And the reason was that it simply is harder to fish or hunt in the ocean. It takes a much more complex suite of technologies to do this effectively. This happened, let's say, about 100, 200 years ago, where we suddenly had the tools to fish in the deepest parts of the oceans, where we're now actually moving into a future where we use helicopters to fish, where we have long lines that reach from Philadelphia that can stretch in the oceans from a distance that is the same as it would be from Philadelphia to New York. We have these robots that we send out effectively into the ocean to locate fish schools, tell us how much fish are beneath them, and then our ships go to collect fish in these spots. So we're clearly transitioned into phase 2, the commercialization, the industrialization of harvest in the ocean. But how about phase 3? How about this switch towards habitat use in the oceans? And I open up in this diagram the possibility of moving towards a kind of an industrialization of use in the oceans. A marine industrial revolution. Note of very importance, I put a question mark behind this, right? What I'm doing is basically asking what is going to be the 50 or 100-year future of the oceans, and scientists, I most certainly will be wrong about some part of this, perhaps a large part of this is a comfortable ground for us. But when it comes to thinking about how to manage the future, you need to actually get some projections for the future in circulation. So let's engage this question. Are we headed towards a 50 or 100-year future where things look a lot more like, the oceans look a lot more like things did on land during the 17 and 1800s in terms of the intensity of this industrialization? Why is this important? This is a record of extinction for animal species. Things are kind of on land, coated in green. Things are kind of cooking along at what could be called a comfortable rate until we get to the Industrial Revolution on land. And then there's this spike. This switch from hunting animals to using and changing habitats almost certainly is responsible for this switch in intensity of the rate of extinction. So if we're going along at a clip that I think we could say at least doesn't get us too worried in terms of extinction in the oceans, if we're entering this new phase, we want to know about it because we don't want to see that same spike in extinctions occur in the oceans. So what evidence might we have that we're switching towards a phase of changing habitats in the oceans? Let's look first at habitat change in the oceans. We'll look second at some of the different ways that we actually use the oceans in an industrial fashion, use ocean space in new ways. Coral reefs. Coral reefs, one of the most iconic ecosystems in the oceans, right? And a reason for incredibly colorful, incredibly biodiverse. I mean, they in fact are so biodiverse that a single reef or group of reefs could house 1 million species. They're also incredibly important to us, right? There are entire nations in the Central Pacific, atoll nations I'm talking about, that are literally held together by reefs, that reefs are the foundation of these countries, right? So what's happening to reefs? If we look at, and I'm only going to be looking about in these projections of habitat change, I'm only looking at things over the past few decades so we can really get a sense of whether something is afoot in the oceans, whether change is happening of the kind I'm describing in the oceans. So since 1990, a lot of noise in terms of what's happening for coral reef loss, but by and large, a signal of loss that at least leaves me feeling uncomfortable, right? This is loss outside of marine protected areas for coral reefs. That's one habitat. Let's try another one, mangroves. Mangroves are our saltwater forests, right? Not so many in Rhode Island, but a whole lot in Florida, a whole lot else in the tropical and developing world. Incredibly important for the places where they occur. First, they're fish nurseries, right? A lot of species that end up on dinner plates in places where fish are the most important, perhaps the only source of protein or nutrition on those dinner plates, begin in mangrove forests. They're also natural breakwalls. And again, because so many of these mangroves are found in developing parts of the world, they're the only breakwalls that coastal communities actually have. They're not doing particularly well. So if we look at things from 1980 onwards, a very steady signature of loss of mangroves, one of the most endangered marine ecosystems on the planet. Yeah?
Could you compare perhaps mangroves to eelgrass in the more temperate areas?
Equally bad. Eelgrass it's a depressing business of trying to describe which ecosystem or which habitat is most endangered. Mangroves and eelgrasses are sort of neck and neck from the numbers that I've seen. How about coastal systems, pelagic systems? Shouldn't it be awfully hard for us to destroy blue water space for life? It should be, but unfortunately it's not. So dead zones, probably something that of course everyone in the marine science community here is familiar with, and those in the public as well. Dead zones are basically this notion that we can kill a section of ocean by drawing all of the oxygen out of it. What happens is you have a bunch of pollutants that run out mostly from excess fertilizers in agriculture into the oceans. You have limiting factors like nitrogen and phosphorus, which cause this explosive growth of things like algae and microbes. You have so much stuff building up at the bottom of this food web, so there's not enough animals in these systems, or we fished out some of the animals that would otherwise consume this bolus or pulse of productivity, so it dies and it sucks out of the oxygen as it's decomposing. So we're familiar with some of the more iconic dead zones, like at the mouth of the Mississippi River, but there are unfortunately an increasing number of dead zones. So we have up to our tally now from 1920s to early 2000s, 400 dead zones have been documented around the world. So some strong suggestion that habitats are changing in the oceans, right? Which in an uncomfortable way may fit this bill of a transition in the way that we use oceans from hunting to changing marine habitats. How about the way that we're using habitats? Are there new industries that are coming online that are using habitats in a way that is wholly new? Well, let's look at a few of those. Marine mining or seabed mining. So this is a totally new enterprise. In fact, it's so new that it's in fact not even happening yet. What I'm charting for you right now, here is the number of seabed mining claims, essentially, mining claims that we've laid out in the oceans. Now, that's probably a pretty good proxy for general interest in what is going to happen in the future. This number, where we're at right now, is over 1 million square kilometers of seabed that have been put inside areas for exploration and presumably on, for those that are productive, to be mined for rare earth elements and other precious metals that you can extract from the bottom of the sea. This is going to be sort of a game-changing industry if it actually goes on, actually sort of takes form as it might, as some of these early numbers suggest it might. The way this works, essentially, is that we're sending a whole mining operation down to the bottom of the ocean. So we're talking about 300-ton robots that are coming off the factory line in places like the UK now that are taking the operation of mining to the very seafloor. We extract ore and a crust in with the same efficiency, with the same volumes as you might extract on land, and process out the most valuable pieces of that. So some of this may begin as early as 2017, right? And so perhaps, again, in a 50-year future, this is something that fits the bill of an increase in the industrialization of the oceans. How about marine energy? We're building power plants in the oceans, and we ought to be building power plants in the oceans. We'll talk about climate change in a section, but the oceans are this vast repository of carbon or free or very low carbon energy that we should be tapping into. However, it means tapping into this energy source means that we're putting a lot of new hardware into the oceans that we never used to have in ocean space. Let's look at offshore wind. Some cases it's above the water, some cases it's below the water. The below water version of this are tidal turbines that we're putting in now in the UK and elsewhere. So since the 1990s, we're now up to thousands of marine wind turbines that are being put in. How many of these numbers that I'm showing you here come from the United States? Zero. Zero come from the United States right now, but an exciting thing, actually, we're talking about this Rhode Island, is that Rhode Island may be the first state to put in some of these offshore wind farm. And as I said, this may be a way for us to wean ourselves from dirty carbon. However, I think it's just very important for us to keep an eye on the fact that if all of us are taking these strategies, there's going to be, as I say, a lot more stuff in a lot more places in the oceans that never was there previously. Marine traffic. We're all aware that we're living in an increasingly globalized world, and globalization, commercialization of increased global commerce means that we have to move a lot of product from remote places to market centers, right? And the signature of this globalization is very well reflected in the amount of port traffic or changes in volumes of port traffic in the past few decades. A very familiar curve we saw in these other industries in the marine traffic industry. And marine traffic, just like land traffic, has sort of similar impacts on habitat. What are those? So invasive species that we're bringing into new spaces, pollution from these large ships that are traversing the ocean. The largest source of pollution in my home, in Santa Barbara right now, is from marine shipping traffic, right? They also run into things. So there's ocean roadkill, right? following this trajectory of increase in volume for shipping traffic is an increase in the number of ship strikes from this global traffic, this increased this increased transport infrastructure that is manifesting itself in our ocean. So it's worth potentially reflecting a little bit with some of those numbers, these sort of previews, if you will, into where industry is heading, and not a preview, but a strong contemporary view of how habitat is changing. It's worth thinking a bit about how well this changing view of the oceans fits this scenario. And again, challenging ourselves whether there is possibility in these different numbers for moving towards an industrialization, a switch towards using habitats in wholly new ways in the oceans. And if that's the fact, it's really important for us. Hopefully this just sort of ingrains itself in our mind that as we engage these new industries, as we absolutely must, and it's not an answer of saying no, it's about engaging them intelligently, that hopefully this, the pathway of this extinction line ingrains ourselves in our mind as we're engaging this new industry. We're basically now sitting on what I would call a extinction cliff potentially in the oceans. That sounds very dramatic, but I've sat on a lot of cliffs, probably you have too, because the view's great, right? And it's a refreshing place to get a little bit of ocean breeze or whatever, a perfectly secure place to be. Ask a guy who's falling off a cliff whether the situation is different, he will absolutely tell you it's yes. We're sitting quite comfortably perhaps on this precipice of change in the oceans. It's a matter of looking forward, challenging ourselves to aggressively look forward at what some of this new change that will be coming down the pipeline in decades and embracing it as cautiously, as intelligently as possible so that we don't fall off this cliff. And what do we have to work with? We actually have a lot to work with. So as I have developed in the first part of this talk, one of the things we really have to our benefit as we're thinking about how we should be engineering and how we should be protecting the oceans is a whole lot of life, right? There's a great difference in the oceans between something like a sawfish, which is a critically endangered marine species, versus something like the iconic dodo, right? A dodo gone forever. If we change our mind and if we change our policy, we can recover endangered species. The raw building blocks of biodiversity are still alive in the ocean, so if we want to rebuild, we can. When you lose those blocks, you lose that opportunity. That's a great thing to have on our side. Not only are there more species in the oceans, they're actually in a lot of the same places that they've always been. As part of this project, we reviewed range contraction of species. So coded here as before, we have terrestrial species in green and marine species, a collection of pelagic fishes, and then things that you sample in troughs in blue. So lots of marine species are showing contractions in range, basically being packed into smaller space. But what's the magnitude of that contraction is what we're showing in this other panel here. So this white bar is the median of this contraction. By and large, these contractions are smaller for some of these marine species than they are for the terrestrial species. Much larger fluctuations for these contractions on land. And so far, there has been much smaller contraction. A way to sort of put this in a different way is that on land we have tigers that have been in Asia contracted from what was 93% of their range has been lost. They've been packed into these incredibly small little pockets of refuges, right? Tiger sharks, if we think of them as the analog of the tiger in the oceans, have lost some of their range, but by and large, they're still out there circulating in the global oceans. So the fact that we have species and they're still occupying a lot of parts of the ocean, also a source of optimism. How about size? Of course, I'm infatuated with size, right? If we actually put a quantitative view of the early portrait and we extend this to the global perspective of what the size structure of mammal communities, how that's changed since the Pleistocene, you see you don't see perfect overlap between these two lines. The red line is the size distribution of mammals during the Pleistocene. The green line is the size distribution of mammals during the modern period. So what we see is a loss of a lot of those big guys that were here on land during the Pleistocene, mammoth-like things, and are now gone from land. Where are we in the oceans? Perfect overlap with this size distribution. That's to say that the mammoths of the oceans are still out there swimming around. The largest, arguably, depending on how you define large, the largest animal that ever lived on the planet, blue whale, is still out there living on the planet in the oceans. So we have that to work with us as well. No loss to this size structure, which may confer a lot of advantages for the resiliency of communities. So what are the solutions? Very quick set of solutions here. So parks. Many of us that do conservation on our land are very familiar. Perhaps the first thing that comes to mind is the notion of parks. That if you want to see wildlife, bear, elk, moose, whatever, you go to a national park, right? That same concept basically works underwater. For those of you in the business here, professionally of doing marine conservation, you know that marine protected areas work equally well underwater. Where are we in terms of our progress on marine protected areas? This is a summary of global progress in both terrestrial and green and marine protected areas. Well, we're behind the curve. Here's the curve for how much progress, how much of the oceans we've set aside for marine protected areas. We're at 3%. That means 97% of the oceans is currently outside of marine protected areas. And of this 3%, quantity isn't always quality. We break down here the different categories. IUCN, International Union for the Conservation of Nature, gives these self-reported characteristics for how good or how good effectively these marine protected areas are for biodiversity. Only this small sliver of the pie, sections 1 through 4, state explicitly that they're there for protecting biodiversity. So a small percentage of a small percentage are already on the books, but we know that these things work. What kind of science can we bring to bear on how to design parks more effectively? Well, this is a question in the paper about looking at how things move. If you want to put boundaries around animals, you need to know where the animals go. This may be an intuitive observation, but it is the scientist's business to actually belabor intuitive observations. What I'm telling you here is that animals of the same size in the oceans use more space than animals on land. And I'm plotting in this graph the median size of marine protected areas. That's that red line. What we see is that by and large, the median size, the most common marine protected area in the ocean is sort of a boutique marine protected area, about 10 kilometers in size. So there's this vast amount of marine biodiversity, those dots, blue dots that you see above the line, that are not enclosed in protected areas. Well, the median isn't everything. There's something very exciting that's happening in the oceans, and that is that we're expanding and including a whole lot of what I call mega marine protected areas. In the last few years, you can see sort of the average size of terrestrial marine protected areas clipping along like this until we get to the early 2000s, and then this vast increase in size. We now have marine protected areas that are over 100,000 kilometers in area, over close to 1 million kilometers in area. That's 400 Rhode Islands. This is less impactful when I'm talking in other states, but it works really well here. That's really encouraging, but it brings forth a new challenge. We have larger marine protected areas which can capture the biology of species that use a lot of ocean, but we need to come up with new tools and new technologies to enforce an area that's 1 million square kilometers in size. That's going to be a new challenge. Another challenge is thinking about the other 97%, 3% of the oceans in marine protected areas. There's a lot of ocean that is not in marine protected areas. We need to challenge ourselves to think beyond marine protected areas. 67% of the global oceans are lawless space. And I promise you that humans act lawlessly in lawless space. So if we appreciate the oceans, as so many of us in the ocean in this room do, we simply can't continue to abide by the notion that the vast majority of this has no law to govern it. Fortunately, just days after we published this paper in Science, there was sort of a change of perspective in the UN. They've been working on this for a long time, but they made a statement that they want to make a binding agreement to revision the way that we enforce biodiversity or manage biodiversity in these international waters beyond our exclusive economic zones. Climate change. I won't spend a lot of time about climate change. A moment though, because all of these other tools that I've described, thinking about zoning in new ways, the international parts of the ocean, or thinking about marine protected areas, will make no difference unless we deal with climate change. Think of it this way. If you have a fish tank and you put a little bit of acid in the fish tank and you turn up the temperature, how are your fish going to fare, right? Not well, right? That's essentially what we're doing to the oceans right now. But what we're discovering in a very exciting way is that there is adaptive potential in the oceans. One of my colleagues on this review actually showed that corals can, certain corals in certain places, show the capacity for adaptation to increase temperature and increase acidity. So it's not a matter of stopping climate change. There'll be some great dialogues this week about how to do that. Great if we can, and we ought to keep that on our target. It's to a large degree about slowing climate change down. If we can buy these animals just a bit of time to deal with this adaptation process, then I think we're in a lot better place for the future. A quick slide about smaller things that we can do in our own lives. I know there's a lot of people here from the community, and it gets a little bit overpowering to think about, well, how do I engage with the global climate change discussion? Well, in fact, there are many things that in our kitchens, in our garages that we can do as we're thinking about how we personally shape the future of the oceans. First is thinking mindfully in the seafood section, which is our portal into the oceans that we encounter week to week in the grocery store, right? In the Santa Barbara fish market, I can buy critically endangered fish species. That's like finding a rhino steak next to your ribeye, right? If you don't know that, that's what's happening in a lot of our seafood sections. There's a lot of wonderful, green, sustainable choices, but then there are a few of these, I was going to use the red herring, I guess that's not. There's a lot of red choices hanging out in amongst these green choices. New tools like my favorite, the Monterey Bay Aquarium puts out a Seafood Watch electronic version of this. You just type in what's for sale. It tells you whether it's green, yellow, or red. Marine plastics. People in Santa Barbara and researchers elsewhere have highlighted this as a major problem. There are 5 trillion pieces of plastic in the oceans. It's hard to even get my head around that number, right? Well, what can we do? We engage plastic consumption in our everyday life. Anything we can do to sort of slow the flow of plastics through our own households and then onto the ocean will make a difference. Carbon, right, and climate change. As I say, it gets overwhelming to think about climate futures at the global level, but 1 gallon of gas equates to 20 pounds of CO2. So we should take this 1 gallon at a time. So the decisions that you make on how you're going to commute to school, run your errands once a week, once a month, can actually start to make inroads in cutting out these gallons, cutting off these pounds. Our state, California, is in the process right now of trying to take on new legislation that will take us a more comfortable position in terms of our carbon emissions. So if we take this gallon by gallon, person by person, state by state, then I think that's where we're going to be able to address this fundamentally important issue. The last thing that I'll point out as a personal solution is engaging next generations, right? Someday I'll be not the young guy, but the old guy up here ranting about the oceans, right? And we need to have a long line of young guys ready to care and get involved in these processes of both studying the oceans and involved in change in the oceans. In Rhode Island, it's perhaps as simple as taking your kids down to the tide pool. In Michigan, Wisconsin, elsewhere, maybe this is the responsibility for the journalists in the group to actually take people underwater with your writing, make them care and aware of the issues that are going on in the oceans. So a summary view of the things that I've said. I was born in LA. A summary view of the things that I've said essentially are that the oceans remain a wilder place than life on land, but it's a precarious kind of wildness. My home was once the Wild West, and that's only a few hundred years ago, right? It was a time when grizzly bears were chasing kids like me around Los Angeles. No more, right? Like, this is the wild version of Los Angeles now. But here's the remarkable thing. You can, and I did, jump on one of these freeways as a kid, run out to the coast, put on a mask, dive off the Santa Monica Pier, and be in the company of 100-pound fish. If you're there in the right time of the year, you're in the company of many thousand-pound whales that are migrating up and down the coast. So there is this great vibrancy of both life, richness, and wildness that's still in front of us in the oceans. And there's a lot of frightening indicators that suggest maybe that wildness is in peril. So to return to this slide, I'd say, the last slide here, I'd say it's the business of actually creating the science for describing this change is something that I take very seriously. And of course, my colleagues in the room take very seriously. I get the opportunity to teach about 150 students a year at UC Santa Barbara, get the opportunity to share these facts, this data, this message with the students. But in sum, it's a very small part of what will be the proper way to engage an ocean future. And one day, one person with one newspaper put this message and this science in front of the same number of people that would take me 400 lifetimes to actually reach in my classroom. So my point, since we're talking a lot about the role of journalism this week in science, is that there is some responsibility on our shoulders for describing these patterns of change, but the grander and the more important responsibility is on your shoulders to actually digest and communicate this kind of science to a broader audience so that there is a way for us to intelligently do something about it. So I'll leave you there.